Hello, everyone. Welcome to Desmos' second webinar. My name is Jason Merrill. I'm a senior software developer here at Desmos, and I'd like to tell you about, in honor of Pi Day. Today's March 14th, 314. I'd like to tell you about making Pi from scratch. So, first of all, what do I mean by from scratch? Scratch means different things to different people, so let's turn it over to Carl.
If you wish to make an apple pie from scratch, you must first invent the universe. Thank you very much.
Okay, so as I said, from scratch means different things to different people, and obviously it means different things to an astronomer than it does to a chef. But for me, what from scratch means is from geometry and arithmetic, so plus, minus, times, divide. So let's get started by talking about what is pi. So pi is the ratio of the circumference of a circle to its diameter, or I'll be talking about half the circumference to the radius for most of the day. And so we're going to follow a really simple method for approximating pi as the ratio of the circumference to diameter of a circle. That was invented by a Greek polymath called Archimedes. So he lived from 287 to 212 BC, about a generation after Euclid. And he had a really simple idea for how to calculate pi. So his idea was that you can approximate a circle by a polygon. And the more sides you have to a polygon, the closer an approximation it is to the circle. So if only you can figure out how to calculate the perimeter of a polygon that is either inscribed or circumscribed in a circle, then you can calculate pi as roughly the perimeter of the polygon divided by the circumference of the circle. So let's jump over to Desmos and explore this idea a little further. So I've prepared a graph here that draws a polygon circumscribed in a circle with radius 1. So this slider here, n, I can change just by sliding it, and it'll change the number of sides in my polygon. So we can set n to 3, and we have a triangle. 4 is a square. 8 is an octagon. And by the time we get to, say, 32 sides, we have a pretty good approximation for a circle. So the equation that I have here for a polygon, I don't want to go into too much today, but it's fairly simple. It's the general way you draw a line in polar coordinates, 1 divided by cos of something, and that something is down here. I'm going to skip that for the moment. So let's talk about how you calculate the perimeter of a polygon, and we'll step up our polygon to an 8gon for now. So we'd like to calculate the perimeter. We want to calculate the side length of this inscribed polygon. So I'm going to try to find the value of a point that is. Can you see my mouse on the screen? Okay, so I'm going to try to calculate the height of the rightmost side. So to do that, I'm just going to go ahead and draw a point. And so the point will have x-coordinate 1 and y-coordinate, well, let's try something. So h, I can always make anything a slider by just defining it. It's one of the really cool features of Desmos. We know it's going to be somewhere between 0 and 1. So I'll go ahead and set that. And so I can slide the slider until the point is about at the vertex I'm interested in. And now, hopefully, we have some more people in the room here. I want to pause for a second to do some administrative details. So I would love to answer questions as you go along. And the best way to ask questions, since we have people watching from all different places, is to tweet your questions at Desmos, DESMOS. So Eli's going to be following the Twitter stream. Ask away, and I will happily stop to answer any questions that you might have. All right, back to finding the side length of a polygon. So if we look at this point that I've just put roughly on the vertex, we know that its x-coordinate is 1. That's the way we set up our polygon circumscribing the circle. And its y-coordinate is going to be the tangent of some angle. So let's change this point into a line here. And one of the easiest ways actually in Desmos to make a line between 2 points is to add a table. So I'm going to slide out my options for more types of equations and make a new table. So I'm going to draw a line from the origin to 1, comma, h. And I can turn on the line here by opening the points menu and clicking connect. Okay, so there we have a line. And so the ratio of the height of this triangle to its base should be the tangent of some angle. And that angle is going to be the angle in the whole circle, which is 2 pi, divided by twice the number of segments, since this is half a segment length. So if we say that h equals tan of 2 pi divided by 2n, then we see that h falls right on the edge of our polygon. And let's go ahead and get rid of those factors of 2. So maybe go to projector mode. And Eli just pointed out to me that it would be easier for everyone to see if we went into projector mode. So this is really a useful feature if you're in front of classrooms too. So this, now h equals tan of pi over n, and this will hold no matter what n is. So there it is for a square. For a square, we see that h is 1, which is probably what we expected. Okay, so now we know how to calculate the side length of a polygon with n sides, and its perimeter is going to be 2 times h, which is actually the length of the side, times n. So the perimeter of a square is 8, and our approximation for pi is half the perimeter divided by the radius. The radius is 1. So we can say that we'll call it p is our approximation for pi is equal to n times h, or n tan of pi over n. Okay, so now we have an approximate value for pi. I'm going to go ahead and drag this equation up to the top so we can see how it depends on n. So if we increase n to, say, 8 here, we start to get a number that's closer to pi. 16 is even closer. And let's just go ahead and make it 1,000,000. All right, so that's a pretty good value for pi. So we're done, right? We have a good answer for pi. Well, no, not really, because if you've been paying careful attention, you'll notice that we actually have pi in our approximation for pi. So if we don't already know pi, then where do we get started? And this is really sort of where the interesting part of what Archimedes did comes in, the real genius of his trick. So what Archimedes realized was that he could calculate the side length of a polygon with 2 n sides if he knew the side length of a polygon with n sides. So to make this concrete, let's go ahead and draw a new equation for a polygon with 2 n sides. So we'll just go ahead and replace 2n there. So what we'd like to do is come up with and let's make one more point here. So point on this polygon 1 comma tan of pi divided by 2n. All right, so we like to calculate this orange point here based on the value of the purple point. So what we're really doing with this calculation here, we're saying since we've doubled the number of sides, we've halved the angle between each of the sides. So the problem here is to figure out how to bisect an angle in a way that lets us calculate the side length. So I'm going to go ahead and switch over to a new graph here and explore this subproblem of calculating pi from scratch. Has anyone been tweeting yet?
We have one person who said that they love projector mode.
Awesome. I guess I'll turn on projector mode in my new slide. Eli says one person loves projector mode. I love projector mode too. All right. So the first thing I'm going to do is go ahead and draw a triangle with base 1 and height h. And again, tables are actually the easiest way, I think, to draw polygons. So we're going to go from 0 to 0 to 1, 0, 1, sorry, 1, 0. And I'm going to go ahead and connect these points here, and we'll zoom in so that this fills up most of our screen. And then 1h and 0, 0 to close it. Now, we can't draw any of these lines that involve h because we don't have h yet, but we can always define it, and then it will be a slider for us. So we'll deal with h between 0 and, say, 2. Well, we'll go 0 to 1. So now we can change h, and it will change our triangle for us. So what we'd like to do is calculate the point on this triangle where a bisecting angle hits it, because that'll be half the side length. And so I don't know when everyone who's watching was in geometry class. Maybe you remember how to bisect an angle. Maybe it will come back to you when I show you. But the first thing to do to bisect an angle is to draw a circle. So we're going to draw a circle around our triangle with radius 1. Doesn't actually matter what the radius is, but we'll use 1 just for convenience. So we've drawn our circle with radius 1, and then we want to find 2 points that hit the circle that are separated by the angle. So we have one of them down here at the bottom of our triangle already, and we'd like to find another one. So let's go ahead and make a new table here for our new point. And so we know that the point we want is going to be somewhere on the top line. So let's just make this an adjustable point too. So its x value is c, that could be anything. And the y value, in order to be on our triangle, should be ch. So I can go ahead and define c. We'll let c slide between 0 and 1. And so what we're trying to do is put c on our circle. Find where the triangle intersects with the circle. So in order to do that, we can say that we basically want to do this as a problem of ratios. So let me add another point actually here to show what we're trying to do. So we're trying to get a line that's a chord on the circle. So it's going to go from CCH to 1, 0. I'll go ahead and connect those. So this value for C that we found by a slider works for this particular triangle, But if we change h, then it doesn't work anymore. So we're trying to find a general value for c that works for any triangle. So we can see that we can do this as a ratio problem by realizing that this distance c, this distance along the base, has the same relationship to the entire base, 1, as the distance along the hypotenuse has the entire hypotenuse. So let's do this as a ratio. C divided by the total base, 1, is equal to the hypotenuse, or the distance along the hypotenuse, which is 1 because it's on the circle, divided by, and what's the total hypotenuse? Well, this is a right triangle, so a squared plus b squared, 1 plus h squared. So we can go ahead and get rid of that factor of 1. And now we've defined c in such a way that it will always be on our triangle, no matter what h is. So that's the first step for bisecting an angle. Now, the second step for bisecting an angle is to bisect the line we just drew. So if you had a compass, you would do this differently. Since we're working in coordinate geometry, we can just take the average of the x and y values of these 2 points. So let's go ahead and draw.
We have one question. How did you know to use c times h for the y
coordinate? So we have a question, which is, how did I know to use c times h for the y coordinate? Well, I have a triangle here. It's really sort of a rise over run problem. So since the base is length 1, that's our run, we just arbitrarily made the height h, so that's our rise. So the slope of this line is h over 1, which is h. So to find points on the line, we just multiply, y equals mx. We don't have a b, so our slope is h, and our x value is c. So all points on this line will be of the form c comma ch. All right, so we're going to make another point on our line here, which is the average of the 2 points that we already have. So it's going to be a half times 1 plus c, and a half times ch. All right, so there's a line on our chord, and I'm going to show you one more trick for drawing lines with Desmos. So we can draw a line through the origin of a point pretty easily with a parametric equation. So parametric equation is, in general, of the form f of t. Well, let's call it x of t, y of t. Since this is a line, it's just going to be linear functions in t, and so we can just, oops. I want to draw a line right through that midpoint that we just found. So I'm going to say a half times 1 plus c is equal to a half cht. All right. Let's go ahead and make that a different color. Great. So now we have a line that hits our triangle right at the point we're trying to find. So this will be the side length of a new polygon with twice as many sides. So the last thing we have to do is find the point on the altitude of the triangle that intersects this line we're after. So first, let me just make another slidable point to emphasize what we're trying to do. We're trying to find a point at 1 comma h. I'm going to call this value h sub 2. And we can define h2 to be something between 0 and 1. And oops, yeah, well, this will work. So we're trying to find this point here. Okay, so now this is one more time a ratio problem with triangles. We want to find the relationship between the blue midpoint that we already have and the red point that we're trying to find. So here we're going to use the fact that h2 divided by the height of our midpoint line, which is a half CH, is the same ratio as the height of our, sorry, is the same ratio as the base length out to the end of our triangle, which is 1, and the x value of our midpoint, which is half times 1 plus c. So let's go ahead and do a little bit of algebra here. I'll copy the denominator up to the numerator here. Cancel some factors of a half. And now I'm just going to go ahead and substitute in our definition for c, which is back here a couple equations up. So substituting in both places for c with 1 divided by 1 plus h squared. Now finally I'm going to move this 1 plus h squared into the denominator. So let's copy that piece, make it a prefactor in the denominator. And last thing is to distribute it through multiplication. So that just gives us a 1 plus h squared. Okay, so we did a bunch of geometry, a bunch of algebra, and we finally get to h2 as a function of h. And I'm just to emphasize that this is a function, I'm going to go ahead and define it again as f of x. F of x equals 1 plus the square root of 1 plus x squared. No, we don't need to see this just yet. Okay, so this is a good point as a checkpoint, because we just did a bunch of geometry, a bunch of algebra. Some of you may have followed this really well, some of you might not have, and that's totally okay. The main takeaway here is that we now have a formula for figuring out the side length of a polygon with twice as many sides, or alternatively, this is actually a half angle formula for the tangent. So we were talking about the tangent of a whole triangle, and now we want to talk about the tangent of a triangle with half the angle. So if you got lost in the last few minutes, that's okay. We're only going to depend on this last result here, and luckily you can look it up on Wikipedia. So let's go ahead and make another new Desmos graph, and we'll just start with only the last result that we had. All right, so our formula was, let's get into projector mode again. F of x equals x divided by 1 plus the square root of 1 plus x squared. So it's a function, looks like this. We can check that it's a half angle formula for the tangent if we want. So it's the tangent of a half arctan of x. There it is. I didn't know that before, but it does what it's supposed to do, what it said it would do on the label. All right, so now we can use this formula to start computing approximations for pi. So let's go ahead and make a table that's going to represent our approximation for pi as a function of how many sides we have. So we started off with a square, and we know that a square has the square with radius 1 has perimeter 8. So this p here, actually, I'm going to use it to mean not perimeter, but half perimeter for our pi approximation. So our pi approximation for a four-sided thing is 4. And I'm going to go ahead and hide f of x there because we need it as a function, not a graph. Now, if we want to know, let's just call this n because it's how many sides we have. And I'll add one more column for p minus pi. All right. So, and just so we know how well we're doing, let's add the line y equals pi. All right, so now we can use our formula to compute the approximation of pi for an 8-gon. So we now have 8 sides that have f of 1 side length. So it's actually, the side length is twice f of 1. Yeah, so, oops. Yeah, this is good. Yeah, great. So now we see that we have a better approximation for pi. And we can make a 16-gon that approximates pi as 16 times f of 1. And now we're doing even better. So we can just repeat this process for as many times as we want. And every time we repeat it, we have an even better approximation of pi. And let's zoom out here a little bit. All right, so for the 32-gon, we are within, we get the first decimal digit of pi rate. I think a 64-gon gets us the second digit. Yep, and we could keep going. So the thing that's really cool about this is that we've reduced, well, what we've done is we came up with not just one approximation of pi, but an algorithm for computing pi. And the more we're willing to turn the crank, the more digits we can get. And this was actually sort of the history of computing pi for 1,500 years or more, almost 2,000 years after Archimedes died. It was who has the most patience to apply this formula? And then in the last 200 years, we've come up with much better tricks. So, all right. So we have a nice simple formula here. It doesn't involve pi anymore. It's just x times 1 plus the square root of 1 plus x squared. Now, I promised you that we would be making pi from scratch today. So there's one piece of our formula that is still not from scratch, and that's the square root here. So this is another thing that I guess I never got to learn in the classroom, but I think is really cool. So we're going to learn how to compute square roots using only plus, minus, times, and divide. So to do that, I'll open up one more Desmos graph. And our goal here will be to calculate the square root of a number, let's call it b. So b can be anything. Let's make it something not too specific. So the square root of b is the number x such that x squared equals b. And Desmos helpfully tells us what that value is. So we could make b 9, and Desmos would tell us. But that's not from scratch. So in order to calculate what x is, we're going to do a little rearrangement here that doesn't seem like it would make a very big difference, but it actually turns this from just a statement of facts to practically an algorithm. So we're just going to divide both sides by x. If x squared equals b, then x equals b divided by x. And let's just plot those two curves. So here's x, here's b divided by x. And let's just go ahead and plot y equals square root of b so we are focused on our target. So these two functions intersect at a single point, and the point that they intersect at is the answer we want. So if we have any value for x, any initial guess, then our answer lies between these two functions. All right, there we go. Lights back on, no problem. So let's take a look at the curve that's the mean of x plus b divided by x. So there it is in green. So we'll call this function of x, s of x. And what s of x is actually another algorithm for calculating square roots. So let's go ahead and let's set b to 2 now. Now that we've seen that all of this holds its relationship no matter what b is. So let's set b to 2. We're going to try to calculate the square root of 2. So we can do this by just, we'll make a table to see how our progress is going as we do this. Oops. All right. So at step 1 of the algorithm, let's just put in b as our initial guess. And so we can measure our progress by looking at y minus square root of b. So now on step 2, we can do s of b. And we see that it's actually closer to the square root than we were when we started. Step 3 is s of b. Step 4 is s of b. Okay, and now we're actually doing so well that Desmos doesn't show us the difference between our answer and 0. It's not quite 0, so we'll add one more column, which is going to tell us how many digits of our answer are correct. So y minus square root b. All right, we'll go ahead and make it minus, so it tells us how many digits we have. So we're actually right to 5 digits, and if we go ahead and do this for another step, we get 11 digits correct. And I think if we do it for another step, we have so many digits correct that the way that our computer represents these numbers cannot distinguish between them. So we don't even get an answer for log, because log of 0 is 0. But we would have something like 22 correct digits. So this is a really cool algorithm. It's called the Babylonian method for approximating square roots. It works way better than it deserves to based on the derivation that I showed you today. This wouldn't work for the average of any two functions. But it's really beautiful and simple, and it only involves simple multiplication and division. So now if we go back to our formula for half angles, we could just use the Babylonian method to compute these square roots. And we've finally gotten to a point where we can calculate pi from scratch. So, of course, there are other ways to calculate pi from scratch. Once you've mastered the beginning, there's any number of variations that use really cool ideas from calculus. This is a nice one, the Mach-in formula, that really was the first one to substantially advance the state of the art after approximating pi with polygons, but it's a little bit harder to see where it came from. Probably the most impressive algorithm for pi that people are using today is called the Chudnovsky formula. It looks like this. It's actually also, sort of from scratch in the sense that it really only involves multiplications and additions, a square root there that you can do just once. But it's pretty hard to connect to geometry. So I hope that that today you've seen some more ways to use Desmos, and that you've come to appreciate a little bit more exactly what it was that Archimedes did 2,200 years ago. And I hope you enjoyed Pi from scratch. Do we have any other questions from Twitter?
We've had a few. I've been answering them as we go.
Mm-hmm.
Someone says, I knew S of X looks familiar. Questions about putting text in graphs, how you were able to make text boxes so efficiently.
Ooh, great. Yeah, so we have a question about how to make text in graphs. So there's two ways to do this. There's this handy menu when you make a new expression that will let you decide expression, table, or text. So I can always click text and then type a message to our fans. The other way that's much faster is when you make a new expression, if you just use the quotation marks key, like you were going to type a quote that somebody said, then that automatically makes the box a text box. And again, the character I was typing is that one, quotes. And you just need one of them. More questions?
Great job, Jason, says Carmen.
Thank you, Carmen. Okay, well, if there's no other questions, then I think I'll conclude Desmos' second webinar, and we should be back in 2 weeks. So thank you all so much for listening, and we look forward to meeting you again.